These are some problems that we've worked on in the problem sets, and I've just chosen a few to do to maybe spend a little more time explaining the algebra and the simplification of certain quantities. I'm going to have to break it up into two videos because I've tried twice and both times the video gets too long and it freezes when I try to publish it. So here we go for the third time. I know that you know how to calculate S3 and S4. You just add up the first three terms and the first four terms. But what I wanted you to notice here is that S4 is equal to S3 plus the fourth term, which would be 1 over 2 plus 3 to the fourth. And in general, Sn is equal to the partial sum right before it plus the nth term of sigma an. So this is an important relationship to remember because it really tells you, it explains the test for divergence. If Sn, if the sequence of partial sums converges, then you know for large N, these two partial sums right next to each other are both very, very, very close to the same number. So an then has to be close to 0, and that gives us the test for divergence. So let's see. This series, I better write it again here. The sum of 1 over 2 plus 3 to the k, and it started at k equals 1. Show that the sequence Sn is increasing. Well, by this relationship that I wrote up there, since A sub n, which is 1 over 2 plus 3 to the n, is always greater than 0, because of this relationship here, we know that Sn will always be greater than Sn minus 1. And that's what it means. Therefore, Sn, the sequence of partial sums, is an increasing sequence. We also know that A sub n, which is 1 over 2 plus 3 to the n, is less than 1 over 3 to the n, which is 1/3 to the n. And we know that that is the nth term of a geometric series that converges. The sum of 1/3 to the n, starting at n equals 1 to infinity, we know that that is actually equal to 1/3, because it starts at 1. This is equal to the first term, 1/3, over 1 minus 1/3. So that is equal to 1/3 over 2/3, or 1/2. So look carefully. The nth term of our series is always less than the nth term of a convergent series, converges to 1/2. And this series too, the partial sums are always increasing. So we know that Sn, the nth partial sum of the series that was given in this problem, is always less than or equal to, in fact, less than 1/2. So this gives us that Sn is increasing and bounded above. So Sn increasing and bounded above implies that the sequence of partial sums converges. And that is Theorem 3 in section 11.1. So if Sn converges, that's exactly what it means for the series to have a finite limit. The series converges. that is, i.e., the sum from k equals 1 to infinity of 1 over 2 plus 3 to the k converges. Because we showed that its sequence of partial sums is increasing and bounded above. In this problem, we're given the fact that sigma 1 over j factorial is e. In other words, the series converges to the number e. So it asks us to find the sum of this series. Well, you can see they look very much alike, so the best thing to do is just to draw out a few terms, to write out a few terms. This series is 1 over 0 factorial plus 1 over 1 factorial plus 1 over 2 factorial plus 1 over 3 factorial plus 1 over 12 plus ... Well, let's write out a few of these. J starts at 0, so this one starts at 1 over 2 factorial. And then we have 1 over 3 factorial plus 1 over 12 plus ... So we can easily see what the difference is here. This one is 2 more than that one. So we can say then that this series is equal to e minus 2. Here we're asked to find the sum of the series, and we see that this is going to be a geometric series, so we will be able to find the sum. So we need to write this expression in terms of a times r to the n. That's the general form, a r to the n. So let's see. Let's take, I'm going to do this in yellow, and then we'll go back. This is just algebra. I'm going to write it as, it's not, oh, by the way, minus 2 to the n is not the same thing as minus 2 to the n. So be careful. So I'm going to bring that minus out. That would be part of our constant. And I have 2 to the n on top, and on the bottom, 3 to the 3n is 3 cubed to the n. And so we have minus 2 over 27 to the n. And this series then, we would rewrite it as the sum from k equals 2 to infinity of minus, that's our a, minus 1, and 2 over 27 is r. It is less than 1, and so this does converge. And it will be equal to the first term. Well, the first term is when k is equal to 2. So it will be equal to, the first term is minus 2 over 27 squared over 1 minus 2 over 27. And you go ahead and simplify that yourself. That is the sum of the series. The next one, it says to find the sum of the series, not to just determine if it converges. So this is certainly not a geometric series, and that's all we know how to sum up. So this must be collapsing. And so let's actually write Sn. I'm going to go up here a little bit because I'll run out of room. So let's write Sn for part B. Sn, and hopefully we'll get a formula for Sn, and if we do, we'll take the limit as n goes to infinity to get the sum. So you know that the natural log of a over b is equal to natural log a minus natural log b, one of the properties of exponents. So we will write this as Sn, well, I'm thinking of the series this way, the sum of, and instead of writing each of these like this, I'm going to write natural log k plus 1 minus natural log k from k equals 1 to infinity. So I'm thinking of the nth term of the series as being this difference of logs, and you can see there's going to be canceling. So when k is 1, we have natural log 2 minus natural log 1. Let's keep our parentheses on. Plus, the next one will be natural log n. K is 2, so we have natural log 3 minus natural log 2. Plus, natural log 4 minus natural log 3. Plus, and now I like to go put the last 3 terms in. So the last 3 terms, well, Sn, so k will be n minus 2. So when k is n minus 2, I'll have the natural log of n minus 2 plus 1 is n minus 1, minus the natural log of n minus 2. Plus, now when we have k equals n minus 1, so I'll have natural log n minus natural log of n minus 1. And then the last term is the natural log of n plus 1 minus the natural log of n. Alright, so now you should be able to see a lot of canceling. And let's see, natural log 2 cancels. Natural log 2 minus natural log 2. Natural log 1 is 0, so we can cross that out. And we see that the first one in each set of parentheses cancels with the second one in the next set. So as we go to the end, we can see that this last one will cancel with natural log n. And the natural log of n minus 1, the second one, will cancel with the first one in the pair before it. And natural log n minus 2 will have canceled in the pair before that. So let's see. Oh, and natural log 4 will have canceled with the one right after, with the second one in the pair right after it. So what we have after you cancel everything out is simply the natural log of n plus 1. That's what Sn is. And if the series converges, it converges to the limit of Sn as n goes to infinity. But the limit of Sn then does not exist. And so we say that the series diverges. In all of these problems, be very careful to distinguish if you are talking about the nth term of a series, the nth term of the sequence you're adding up, or the nth term of the sequence of partial sums. So here we're asked to show that the nth term of the sequence of partial sums is between these two quantities for given any n. Well, if the limit on the left-hand side is the same as the limit on the right-hand side, then we can conclude by the squeeze theorem for sequences in 11.1 that Sn converges, and so the series converges. So let's look, let's just calculate these limits. I'll do that in yellow. This on the right-hand side is 3 plus n over e to the n, and we know that e to the n grows at a much faster rate than n, and this goes to 0. So the limit on the right-hand side is 3. Now let's take the limit of this one. I'll go down here under A and take that limit. We want the limit of 6 natural log n over natural log n squared plus 1. Now, both the numerator and denominator get large without bound. They both go to infinity, right? So we can use L'Hopital's rule. Now, I wrote in the limit, so I'm going to use proper notation and not use those arrows that I always use. This will be equal to the limit, using L'Hopital's rule, of 6 over n over 1 over n squared plus 1 times 2n. So if you simplify that expression, actually I said I would do all the algebra here, so let me do this. We'd get the limit of, now this is 2n over n squared plus 1, so I'm going to invert and multiply. So I have 6 over n times n squared plus 1 over 2n. Now, this, if you use L'Hopital's rule once, or if you divide top and bottom by n squared, you'll see right away that this limit is 6n squared over 2n. It is 3. So you just multiply this together and either divide by n squared on the top or bottom, or use L'Hopital's rule again. You get the limit of 3. So therefore, this series does converge, and it converges to 3. This Sn has a limit of 3 by the squeeze theorem, and that means that the series converges to 3. Now the next part says, if anything, could we say something about b sub k? We weren't given b sub k. We were actually given a formula for, or we were given enough to determine the limit of S sub n. But we know that since the series converges, we know that b sub k has a limit of 0. The limit of b sub k as k goes to infinity is 0. And you can go back to the test for divergence and see exactly why that's true. Now, in doing tests for convergence, we have 3 tests. We have the test for divergence, but we have 3 tests for convergence: the comparison test, the integral test, and the ratio test. And they are all for series where the nth term is greater than 0, or non-negative. Okay, so what you do, this looks like a p-series. Let's write down the 2 series that we know about. We're always hoping to compare to either a r to the n that converges when r is in absolute value less than 1, or 1 over n to the p, a p-series. And we know that converges when p is greater than 1. So these are going to be our sigma b sub n's. We're always hoping to compare to one of those. So look over here and say, well, what after n is 40 billion, what's the most powerful thing? Well, it's the n squared. This makes little difference. So you just kind of ignore it. I'm not really crossing it out, but I'm just ignoring it. And we can see that what we're going to compare to then is a p-series, 1 over n squared, and we know that does converge. But we need the right inequality to be able to conclude that this one converges. So start with the denominator. N squared plus the square root of n is certainly bigger than n squared. They're positive, so the reciprocals, 1 over n squared plus the square root of n, is less than 1 over n squared. And there we have it. And sigma 1 over n squared converges. And I could just say p equals 2 to tell me, you write that to tell me that you know you're comparing to the p-series. Therefore, the given series converges by the comparison test. The next series, well, the 3 to the k. 3 to the k is far more powerful than just k, so the comparison series that we're hoping for would be sigma 1 over 3 to the k is 1/3 to the k. And we know this is geometric and it does converge. So we need to have the right inequality, though, before we can say this one converges. So again, start with the denominator. K plus 3 to the k is certainly greater than 3 to the k. So the reciprocal, since they're both positive, 1 over k plus 3 to the k is less than 1 over 3 to the k, which is 1/3 to the k. And sigma 1/3 to the k converges. And we could say absolute r less than 1. And then I know you're comparing it to the geometric. Therefore, the given series, sigma 1 over k plus 3 to the k, also converges. by the comparison test. Again, we do the same thing. We know that this plus 1 makes not a hill of beans difference after k is big. So I'm thinking, well, what is this? That would be sigma k over k squared squared is k to the fourth. Oh, that's sigma 1 over k cubed, a p series. That's what I'm hoping to compare it to. But I need the right inequality. So again, I start with the denominator. K squared plus 1 squared is greater than k squared. So the reciprocal, 1 over k squared plus 1 quantity squared, is less than 1 over k squared. Oh, excuse me. I wanted k to the fourth here. I'm sorry. I crossed out the plus 1 and forgot to square it. So this should be fourth. I hope you see that. I meant to ignore the 1, and I needed to square this, and I didn't. It's true it was greater than k squared, but that's not going to give us what we need. Okay, so let's see. Let's multiply. We don't have this yet, and we want to have this right here. We have to have a sub k less than 1 over k cubed, hopefully. Well, let's multiply both sides by k. K is positive, so I can multiply both sides without reversing the inequality sign. And I get k over k squared plus 1, the quantity squared, is less than k over k to the fourth, which is 1 over k cubed, exactly what we want. And summation 1 over k cubed converges. P equals 3. Or you could put p greater than 1. Therefore, I would say that this given series converges by the comparison test. Well, here we have factorials, and so we'll use the ratio test. And on this one, it's just very important to keep your parentheses on and to be careful. You want to put in m plus 1 everywhere you see m. So we have m plus 1 factorial over 2 times m plus 1. Now, if I just put the factorial like that, that's no good. I need to have parentheses around this because 2k factorial is not equal to 2k factorial. Not equal. You check that and make sure. Let k be 4. 2 times 4 factorial is not the same thing as 8 factorial. So you need to be very careful. And now this is over m factorial over 2m in parentheses factorial. Now I usually skip this step and just instead I write m plus 1 factorial over, and since I have written it once, I'm going to write this out as 2m plus 2 factorial times, and inverting, 2m factorial over m factorial. Okay, well, in yellow, I'll expand this a little bit. I know that the m plus 1 factorial over m factorial cancels because this up here is m plus 1 times m factorial. So the m factorials cancel. Now down here, it's not quite so simple, but let's just write out a few of the factors of this factorial. 2m plus 2, 1 less is 2m plus 1, 1 less, 2m factorial. So these cancel. And we have then something that hopefully we can take the limit of. We have just plain m plus 1 on the top, and on the bottom we have 2m plus 2 times 2m plus 1. Well, actually 2m plus 2 is 2 times m plus 1. this I could write as 2 times the quantity m plus 1, and I could just cancel the m plus 1. And this is simply 1 over something getting large without bound, so the limit is 0. That's our L in the statement of the ratio test, and it certainly is less than 1. So this converges, this series converges by the ratio test.